He'll be telling us about understanding quenching with empirical models.
All right, so it's obvious my previous title was a little bit too long. I just wanted to give you guys an update on empirical modeling, how it's progressed since I last spoke at Santa Cruz Galaxy Formation Conference. I want to really push the boundaries on what you think empirical modeling is. So a lot of you are familiar with abundance matching, but empirical models are much more general than that. When you observe something or measure something in astronomy, it's often not the direct question that you want answered. So empirical models at their heart are a way of getting at an underlying question that you can't measure directly. You're probably familiar with abundance matching or abundance modeling, in which the question is the stellar mass halo mass relation with redshift, and the data constraint is galaxy number densities as a function of stellar mass and redshift. And so the way you proceed is you guess what the stellar mass halo mass relation is, use a halo mass function to predict what you see for number densities, and then how far off your guess is lets you refine your prediction over here. And so then you iterate until you converge on what's the stellar mass halo mass relation that is consistent with your observed data. So going beyond, you could imagine putting a different question over here and different data constraints over here. For example, what is the quench fraction as a function of halo mass and redshift? And as your data constraints, you might have the quench fraction as a function of stellar mass and redshift. So if you guess something over here, you can make a prediction for over here and continue guessing and checking until you refine your model for what the quench fraction is as a function of halo mass and redshift. But empirical models are now so advanced that we can ask much more detailed and interesting questions. And so the one I'm telling you about today, we can ask the question, what is the star formation rate as a function of not only halo mass and redshift, like we were able to do before, but also what's the relationship with mass accretion history? And so now, of course, we add in a lot more constraints. Besides the stellar mass functions, specific star formation rates that we had before, we also add in quench fractions, conformity, and things like correlation functions of galaxies split by their star formation or quench status. Okay, so one brief aside on parameterization. How do I write down even star formation rate as a function of halo properties? Which halo properties are the best to use? Basic parameters are mass, redshift, and mass accretion rate. I think slightly better ones are probably Vmax, change in Vmax over dynamical time, and redshift. But talk to me about that if you're interested in that much detail. At a basic level, if I have a halo of a given mass, or Vmax, and redshift, then I expect there to be a distribution of star formation rates in the galaxies that reside in those halos. And I'm just going to assume that this is a Gaussian, or a double Gaussian. So if I look at the probability distribution of star formation rates as a function of star formation rate, you have some things on the main sequence that are star forming and some things that are quenched. So how do I parameterize a double Gaussian? You need a few numbers. One of them is a location of this star forming peak. So what is the star formation rate of galaxies on the main sequence for a given halo mass or Vmax and redshift? What's the width of that Gaussian? What fraction of things are in the quenched versus the star forming peak? What's the width of this quenched thing? And also, what's the location of this? Turns out, what's the location of this and what's the width don't matter too much because A, we can't measure them observationally that well, and B, as you might guess, most stars are not formed when galaxies are quenched. And so integrated properties like stellar mass or average things like average specific star formation rates for galaxies of given stellar mass don't actually depend on detail on what the exact numbers for the peak, location, and width are. Anyhow, so these are the main numbers, the quench fractions, star formation rate of this peak, and the width here that I parameterize. And I just then want to figure out how those depend on Vmax, redshift, and so on, as well as mass accretion history. So once I have, as a function of halo mass and redshift, what this looks like, if I have a guess for this, then what I can do is make a connection to halo mass accretion. So that different halos will, of course, have different mass accretion rates and different formation timescales. And what I can guess is that the most star-forming galaxies are then in the late-forming or halos with the most highest mass accretion rates, and vice versa. The halos that are getting stripped are hosting the quenched galaxies. But I can tune this. And so it's an open question, what's the best way to assign? So you could imagine that there's absolutely no connection between the star formation rate of the galaxy and the mass assembly rate of the halo, in which case you would just distribute. You would pick randomly for each halo a galaxy from this distribution of star formation rates. Or you could imagine that it's completely correlated, that the most star-forming galaxy that you see is always in the halo with the highest mass accretion rate. And that gives you a very different prediction than for statistics like two-point clustering. Okay, so anyhow, if you pick a guess for star formation rate as a function of halo properties, mass, redshift, and mass accretion rate, then you can go to an n-body simulation, and at every redshift and for every halo, you can assign a star formation rate. And you can integrate along merger trees in the simulation to self-consistently assemble stellar masses for the galaxies in these halos. And so to take a step back, if you're asking yourself, well, what's the difference with a semianalytic model? The overall machinery is very similar in terms of we have a star formation model, and we put it through halos, and we get stellar masses and star formation rates. The main difference is we don't put in physical assumptions for what this looks like. We just ask, what can the observations tell us about what the scalings are? And we don't assume that there's supernovae or AGN or whatever. No, all that's out the window. We just say, there is a functional form with a bunch of parameters, and we let the observations say, what are the allowed ranges? Okay, so then it's standard stuff. If we have halos with stellar masses and star formation rates, we can make predictions for observables like stellar mass functions, correlation functions, weak lensing, add in observational biases and compare with the real things, and then repeat. And so what I've just described to you is a machine where you put in a guess for what the empirical relation is between star formation rates and halo properties, and you get out a mock universe, which you can compare with data. So of course, I've called this the universe machine. And that's all that it is. You start with an empirical model, a guess for how star formation rate depends on halo properties. You put it through compared observations, and then you repeat to refine what are the empirical models most consistent with observations. And so you get out positions, redshift, stellar masses, star formation rates, star formation histories, colors, a lot of things, a lot of basic properties of galaxies, so that almost any crazy statistic that you want about galaxy formation that you can measure from real observations, you can also apply it to this and ask, is your particular model consistent with that particular observation that you want? So conformity or two-point statistics or group catalogs or any wild ideas that you have for how to constrain galaxy formation, you can put as a constraint into this model. Okay. I'll skip this in the interest of time. I'll just say that this thing is fast. It can run on lots of processors. Okay, so also it works. So here's all the data that I'm putting in as constraints. And so the star formation rates as a function of halo properties that I get out can then create a universe that matches stellar mass functions, quenched fractions, specific star formation rates, cosmic star formation rates, and also two-point correlation functions split by quenched and star forming, different masses, also weak lensing, also the new statistic, which is the fraction of star-forming centrals as a function of number density of nearest neighbors. All of these things we can now match. And so I just want to say a little bit about the preliminary results. So we're still doing a lot of analysis and figuring out what's the best way to present the results that we have, but I'll just briefly say a few things about quenching. So as before, we can get results on what is the star formation rate as a function of halo mass and redshift. We can also say what is the fraction of things that are star forming and not star forming as a function of halo mass and redshift. So that's shown here. Halo mass is on this axis, redshift is on this axis, and then these white lines show you typical halo growth trajectories. And so one thing that jumps out right away is that the transition between half star forming and half quenched as a function of halo mass changes with redshift. And so this is suggesting that it's not just a transition between cold halo and hot halo, which would occur at roughly the same mass, but there's actually some other physics because there's a different redshift scaling in the transition between star forming and quenched. Thanks. So things up here are still mostly star forming, even though they're inefficiently doing so. And it's not until they get to much higher masses that they quench completely, is the statement from this. So one other interesting thing that you can see about this is how permanent is quenching in galaxies? So for most galaxies, it is permanent. So let me just quantify that. So for high mass things, they very rapidly transition between 100% star forming and 100% quenched. Low mass things have a slower transition, but here what happens is most of the quenched things are satellites which quench permanently. You don't get rejuvenation. But for a particular halo mass range, which corresponds to a stellar mass of about 10 to 11 solar masses, you actually see a very long transition time between 100% star forming and 100% quenched that takes a very significant fraction of the age of the universe. And over this significant fraction of the age of the universe, a lot of things can happen to halos. So if you have mass accretion events or anything that changes on the scales of a dynamical time that might affect whether the galaxy is star forming or not, means that you can have many transitions then between star forming and star forming and quenched again. So it's actually a very generic prediction for halos, for galaxies of mass 10 to 11 solar masses, that you have many transitions in their history of being star forming and then quenched. So if you just follow, say, this red bold line, you can see star forming, quenched, quenched. And these other ones are also the same stellar mass at pi redshift 0. So you can see also spikes or transitions in many of them between star forming and quenched and back again. So I'll just finish and say empirical models are no longer just abundance matching, but they can tell us interesting things about galaxy assembly quenching constraints, and in the future, much, much more.
Good. If we can have the next speaker up.
My question relates to your last slide,
Sure.
which seemed to show the life histories of individual objects.
Yes.
So you said something very important earlier. You said, I'm going to load up these properties in a self-consistent way
Yes.
that reflect a merger tree history for every object, right?
Yes.
I'm just verifying that that's what you did, and I'm trying to figure out how hard that is. Is that really the trick of the wrist here in doing what you've done?
You mean how hard it is to follow things through?
Right.
It's not hard for an individual model. So it takes about 1.5 CPU hours, but it's hard if you want to cycle through many.
Keep the microphone for a while.
Okay.
Questions.
Okay.
Good. Go ahead. Sorry, Sandy.
Hey, this is really exciting stuff. I think so this thing of it's the same slide that I'm talking about really. The idea that individual objects have to quench and then unquench fits in very, very nicely with what we're seeing in simulations, but I didn't quite understand what is the actual observational piece of data that is telling you that about individual objects. Where is that actually coming from in your models?
Yeah, so the piece of observational data is if you need a correlation between halo mass assembly and whether the thing is star forming or quenched, then you're forced to have this oscillation. And so where does that first statement come, the fact that you need a correlation between halo mass assembly and whether it's star forming or quenched? That comes from the separation in quenched versus star forming correlation functions. So if you have absolutely no correlation with halo mass assembly, then your satellites are quenched at the same rate as your centrals. And so you get very little offset then between star forming and quenched correlation functions. If you have a lot of separation, then that implies a higher correlation between mass assembly history and quenching, which then must give you, in the past history of these things, transitions between star forming and being quenched.
Let me sharpen this question a little bit more. So I'm trying to understand. It's telling you that you don't have all of the galaxies at a given halo mass becoming quiescent at the same time, that it's an extended, but it still wasn't apparent from this why you were so excited about the idea of individual objects rejuvenating. Presumably in your model it's degenerate, and so this is more a statement of, so I just want to understand, what do you have evidence for from your framework, and what is it that you're kind of thinking is reasonable, but you really isn't obvious from
you
your
can
model?
imagine models which are consistent with the universe, such that you quench one time only and that's it. But it's actually very hard to construct these in such a way as to give you both what we see with the clustering as well as only quench once. So it's not only the clustering, I should say, but also things like two-halo conformity, which suggests that there's also a correlation, even for central galaxies, not just satellites, between their mass assembly history and whether they're quenched or not.
Just, can you get any information on the structural properties of the galaxies during these oscillations? Do you get any correlation between structure and quenching?
Yeah, so size and morphology are not in the model. So that's why I said in the future there'll be much, much more.
I'm coming. Avishai was first. God, you guys are giving me some exercise.
It's really exciting to see this growth of the critical mass for quenching with redshift, which is naturally expanded, as you know, by the penetration of cold streams, being much better at high redshift than low redshift. And in fact, this curve was predicted.
Mm. Well, we should talk more. Yeah, we should definitely talk more.
Sorry? It was published long ago. Yeah. 2006, before your time.
So we're co-authors of the paper where we suggested that for star-forming galaxies, the star formation rate can be strongly affected or even controlled by the mass accretion rate of the halo. That's one of the things you tested, but you didn't say in your preliminary results how well that worked. How well does it work?
Yeah, so for low-mass galaxies, it actually works quite well. So we seem to require a very strong correlation between star formation rate and the mass accretion rates.
Of course, for higher mass galaxies, we start to get quenching.
For higher mass galaxies, it's hard to tell because of the data that we have. At redshift 0, it may not be as good, but at higher redshifts, once we get clustering results from Primus, then we'll know.
Okay, great, thank you. So next up is Aldo Rodriguez Puebla, who'll be telling us about the stellar to halo mass relations of local galaxies, but segregated by color.
Hello. Okay, it worked. Okay, thank you very much. So I'm Aldo Rodriguez Puebla. I'm a postdoc here at UC-HiPACC. The work that I'm going to present today, I think it's quite complementary to what Peter presented. So my question is whether the stellar to halo mass relation depends on color. So I did this work with Vladimir Avila-Ruiz at University of Mexico, with Xiaohu Yang at the Jiaotong University in Shanghai, Sebastian Foucault, Yipeng Jing, and Nip Drury at the McDonald Observatory.